Okay. So here's what the properties say. Here's what the properties say. If you're given clues, which you totally are down here in this example, you're given a clue about, like little Blue's Clues, about the limit as x approaches c of f of x is 3. You don't know who f of x is. You don't have a graph. You can't put it in a table. You can't write out the function. You have no clue about anything but this fact. You also know this fact about g. No clue about who he is, what he looks like, what his table or his graph would come out to be. I just know that as I approach c from either side, this guy's going to 6, and as I approach c from either side, that guy's going to 3. I can use this whole table of properties to let me make some jumps. And so here's one jump. If I need to know the limit as x approaches c of -2 g of x, this would be called a scalar multiple from our previous experience with vectors. Scalar multiple, a constant or a scalar being multiplied by, that's right here. Scalar multiple says, oh, this is easy. Just take the b and multiply them by the limit of your function. So who's the limit of the function in this one that I should multiply -2 by? 6. Good. So the final answer is just -12. Dun, 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 dun. Easy. Letter B, there's a property for that. It's called summer difference property. And the summer difference property says if you need to take the limit as x approaches c of f plus or minus g, just figure out the limit of f and the limit of g and put them together. So, who's the limit of f? Who's the limit of g? It's easy. Fine. Is there a property for letter C? And the answer is yes. Quotient property, good. Divide it by 6 and then reduce it 1/2. You got it, Anna. 3 divided by 6, which is just 1/2. The properties probably looked kind of daunting, but they're actually allowing us to make some pretty quick jumps as far as solving, which is kind of cool. And letter D, okay, he's a little weird. There's no square root property, but what property can we use? Power. Because the square root is what power? 1/2 power. If it was a cubed root, 1/3, fourth root, 1/4. So the square root, 1/2, that means I can think of this guy and say, oh, take the limit of f, in this case, yeah, good, of f, and raise it to the power, which in this case, raise it, well, take the square root of it. So the square root of f, f's limit is 3, yeah. It's not nice, it's not pretty, so we're done. Dun, 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 dun. Right? That wasn't bad. So go ahead and go grade our homework. I think there was an even that was one of these. You can go ahead and check it out and see if you got it. But you can also see if it makes more sense now. So section 12.1, let's leave that one maybe for practice tomorrow. I think I have 2 pages of these evens. Let's start with this page. You guys can check your vocab in number 2, your tables in numbers 8 and 16, and the answer from the graph in number 24. Section 12.1 was all about limits with tables and graphs. Limits with tables and graphs. Now, how bad was the decimal in number 8? In number 8? Wasn't it just looking like 0.333333333? Like, okay, 0.3333 is 1/3. Nah, easy. They're unanimous. They're in agreement. So therefore, the limit existed and the limit was 1/3. This whole thing is saying the limit's not reached because if you plugged in 2, there'd be an error. But remember, that's not the point of a limit. The point of the limit isn't what's at 2, it's approaching 2. And they were in agreement, 1/3's the answer. Now, how bad was the decimal in number 16? Yeah, it was super weird. So pause. Look at what you figured out. Were you able to figure out that it was negative 0.0625-ish? Cool. For those of you that said yes. For those of you that said no, well, hold on. Are we doing okay with putting it in our calculator and typing in the numbers they told us to type in and just writing down what's left? If so, then you should have been able to look at it, and when you plugged this one in, you're like, okay, well, and then plugged this one in and compared and said, well, they both have negative, they both have 0, they both have point, they both have 0, they both have 6, they both have 2, they both have, he has 52 and he has 48. Well, what's in between 52 and 48? 50, right? So hopefully we could have gotten at least the negative 0.062. And if you looked, 5 seems kind of in between, so that's why I just said 5. Now, I know it was confusing. Maybe you didn't get the negative 1/16. This type of problem is not well behaved. It's super not well behaved. At 2, it's fine everywhere else, but at 2, it's a little dangerous. So we wouldn't know how to solve this one yet. We're going to learn how to do it in section 12.2. We're going to learn how, by just kind of playing with it, simplifying it, we can get -1/16, so we won't have to do this crazy table thing. So remember, the table thing isn't for forever. It's just for right now. And for right now, it's just helping you guys get the idea of, I don't care what happens when I plug in for limits. Sometimes it helps and sometimes it doesn't, but what I care about is the approach. What I care about is the approach. And yeah, they were approaching the exact same thing. And yeah, it was a weird decimal. So if you got this, you're good. Does that make sense? Okay, and if you got confused by this, I understand. There's going to be a better way of solving as soon as we get to section 12.2. Why did this limit not exist? They weren't going to the same place, right? The two cars weren't approaching the same destination. We're not even going into who had breakfast and who didn't. Just they weren't approaching the same place. Good. Some more evens. Let me give you a little bit of time. I know they gave explanations. I'm just trying to show the long story short of it. And for those of you that got stuck on 42, just think about what we did a second ago. You should have the directions, the problems written down. Just peek and say, wait a minute, so all I have to do is plug in the clues to the math? The answer is yes. (28) and 30, they both didn't agree, right? I think 28 and 30, they both didn't agree. 28 was a lot like that one we did in our calculator yesterday where we had -3 and +3. It was like that. They didn't agree. The two one-sided approaches didn't agree. And number 30. Number 30 didn't agree either. It was coming towards a vertical asymptote, which was weird, but still as you came towards the vertical asymptote, since they didn't agree, just like our notes showed, the limit does not exist. This one was well-behaved, plug in. This one was well-behaved, plug in. These ones were, well, kind of well-behaved, but the property said, sweet, plug in the limit of that guy, which must have been 5, the limit of that guy, which must have been -2, and then do the math to it. Done. Plug in the limit of f, the limit of g, since they're both with the same x approaching a or x approaching c, and do the math. Done. Plug in, do the math. Done. Plug in, do the math. Done. Why was this guy a little bit harder? Yeah, I mean, it's still just plugging in, right? I mean, it's just plugging in, but what was hard was the arc cosine. So remember, isn't arc cosine the same thing as, who's this guy? Cosine inverse. And remember, cosine inverse goes backwards and says, when does, for what theta does cosine equal 1/2 in between 0 to 2 pi? Sorry, 0 to pi. Well, cosine's not positive in the second quadrant. Cosine's positive in the first quadrant. And cosine's going to be 1/2, either memorizing at 60 degrees or pi over 3, or thinking about your cheater chart and saying cosine, well, isn't he the second one? Sine is 1, 2, 3, and then cosine is 3, 2, 1, starting at 1, ending at 0, all over 2 and square rooted. Square root of 1 is just 1. So when is cosine 1/2? Right here. At 0, 30, 45, 60. What's 60? Pi over 3. Or you could have done it in your calculator, cosine inverse of 1/2, I suppose. They did put the decimal 1.0472. Any questions on evens or odds? I'm ready. Any questions on evens or odds? Sweet. What was super nice about the end of homework? All you had to do was plug in. And why was it nice? What was the description I gave yesterday to the ones where you can just plug in and be done? Well behaved. Well behaved. Doesn't even need to be well behaved all the time. Doesn't need to be the perfect model child no matter what. Just the ones that are well behaved around the actual place that x is approaching. So section 12.2 says, what if they're trouble kids? I mean functions. What if they're having some issues? I'm going to take away some of these practice pages just because we did an example of that guy. This guy we might come back to. He's a good practice problem, but not for today. We've done a lot of examples and taking notes and whatnot. So let's just jump into 12.2. The nice thing is 12.2 says, hey, a direct substitution thing. Yeah, that's the first step to always, 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 always try when trying to find limits by hand. Not by your calculator, not by a graph, not with a picture, not with a table. But trying to find the limits by hand. The first thing we always want to try is direct substitution. But what I was saying is, well, 12.1 showed us direct substitution. It was easy, and we liked that. So why on earth is there another section? Well, because not every function is well behaved. It doesn't even mean that they're utter failures. It just means they have some trouble spots. And maybe the limit is pointing out that trouble spot. So if you want to, for section 12.2, you can put up at the top. It's kind of answering the question, what if you plug in and you get 0 over 0? What to do if you plug in and you get 0 over 0? What to do if you plug in and you get 0 over 0? After you guys finish writing this page, the only thing I'm going to fill in is that very, very bottom part. After the colon, I'm just going to fill in something super small. But otherwise, no need to skip lines. But after you finish writing the page, check out the front board. Because there are two different ways that plugging in can be a problem. Both of them have denominators of 0. Both of them have over 0. Both of them have denominators of 0. Both of them have over 0. But they're very different in what they mean and what they point to and what they indicate about the function. And they're very different in what their answers might be. And what this entire section is dealing with is not the number over 0 part. What this section is dealing with is just the 0 over 0 part. So we're not even handling all the types of problems that can occur. We're just dealing with one specific type. So there are other problems that can happen, but we're going to deal with the majority of them. The 0 over 0s. This kind of goes back to chapter 1 where we were first talking about discontinuities, removable and non-removable discontinuities. I think it was chapter 1, chapter 2, somewhere in there. Removable and non-removable discontinuities. We talked about vertical asymptotes versus holes, and as you guys look up at the front board, some of those are vertical asymptotes and some of those are holes. Or I should say one of them indicates vertical asymptotes and one of them indicates holes. So the left side, the indeterminate, the 0 over 0. If you want, you could also put, for section 12.2, we're basically dealing with holes. But as you guys look at the pictures on the board, what I'm showing down here at the very, very bottom is if you plug in 0, 0, you don't still necessarily know what your limit is. You know your function is discontinuous. You know your function has a problem. He doesn't have a nice, pretty point that's just chilling there. But you could still have a limit. How can you still have a limit if the whole looks like this or if the function looks like this? Why does the limit still exist? Yeah, because they're going the same place. It doesn't matter that they're not getting breakfast. They're still headed to the same place, right? Or I should say, here we go. They're still headed to the same place. So the limit still exists. This one, the limit is going to be an actual number. But if the graph looks like this, all right. The limit's not going to exist. Why? The approaches don't agree. Does that make sense? So if you have 0 over 0, you can either have this type of answer for a limit or that type of answer for a limit. And we're going to see today how we can tell the difference. Now over here, number over 0 points to a vertical asymptote. Number over 0 points to, as the graphs come in, as the two guys approach the time they're supposed to meet, they can agree going to infinity. They can agree going to negative infinity, or they can disagree, which means the limit does not exist. But if you guys notice, yes, they both have the possibility of not existing, but their answers, if they have answers, will be very, very different. Vertical asymptotes, if they're in agreement, will only have infinite answers, either up or down. Holes, well, they could actually have a numeric value if they exist. Or I shouldn't even say they could, they will have a number answer, not an infinity, but a number answer if they exist. Now here's one more thing we should probably write down. Holes are called removable discontinuity, which gives us the idea maybe we can do something. Maybe we can do something algebraically. Hey, that's the title, right? Finding limits algebraically. Maybe we can do something to remove the hole, to ignore the hole, to not think about the hole. And if we didn't think about the hole, if we just said, forget it, I'm not even looking at the hole, could we tell without even knowing exactly whether it's a hole, whether it's not? Can we tell if they're going to the same place? Yeah. So we don't even necessarily need to consider the hole. We actually need to get the function to ignore the hole and say, I just need to know what's going on either side. And then I'll be able to know whether or not the limit exists. For vertical asymptote, sadly though, this one's called, if you guys remember, if it's not this, then it's, if it's not removable, then it's, you're trying to figure out how to say it, non-removable. I guess you could say that's kind of awkward though. Vertical asymptotes, there's no math that we can do to really make it any better. It's kind of like it is what it is. There's not really any math that we can do. Non-removable, you're stuck with it. There's no way to, in a sense, reduce out anything to make it better. So we have to just say, okay, well, we know it's a vertical asymptote. Let's try to do some playing around with the function to figure out which case it is. But nice thing's nice. The nice thing is section 12.2 kind of ignores this one where it's non-removable and we have to kind of just memorize and study some stuff. It's instead focusing on this one where we can play with the math and we can play with the algebra and we can figure out more than you would think. So therefore, you guys need to get stuck? Yeah, you, go ahead, the cart's over there. Actually here, let's bring the cart here. Yeah, you're welcome. Here's the cart if anybody needs anything. Sorry, AP Calc just got out. You guys need anything? They're still breathing, that's good, right? They seem a little like... Okay. So, coming back. They're probably going to keep trickling in and out, just ignore them. What I need you to fill in at the very, very bottom is 0 over 0. Step 1 says plug in. If it works, great, you're done. Haha, we liked that. It was section 12.1. That was the best part. But number 2, and actually the whole rest of section 12.2 basically says, what if you have 0 over 0? And here's the long story short. If you have 0 over 0, and I'll put for this one for dividing out, with polynomial numerators and denominators. Okay? If you get 0 over 0, if you plug in and get 0 over 0, and you have polynomials on top and polynomials on bottom. If you get 0 over 0 with polynomials on top and polynomials on bottom, this is what you want to do. You want to try the dividing out method. That's one way of putting it. You can say it lots of different ways. But the dividing out method. Now hold on, pause. Before we go any further, I just want to give you a quick, at the very, very beginning of 12.2, if you plug in, if you get 0 over 0, you're not done. So I want you to write, literally, keep going. If you were to ask any of my Calc A, B, and BC kids, maybe not right the second, let them rest a little bit, but then you were to ask them, what do you do if you get 0 over 0? They should all say, keep going. Why? Because I drill it in their heads. Why? Because 0 over 0, you're not done. 0 over 0, there could be an answer, so keep going. How? Play with it. Play with what? Play with the function. Well, how do I play with the function? Here you go. If you have polynomials, tops and bottoms, you're going to play with the function by trying to factor. And if factoring is too scary, by polynomial division. So, check. First thing, plug it in, plug it in. Let's hope it's as nice as the 12.1 ones. Now, some of you are like, I don't think it's as nice. It has a denominator. But wait, if x approached anything but -3, it'd be fine. If x approached anything but -3, it'd be fine. What's the dilemma, though? X is approaching -3. Okay. So it's not fine. But pause. Remember, it could be not fine 2 different ways, and we have to figure out which one it is. So, yeah. For those of you guys that can do quick mental math, -3 squared plus -3 minus 6 all over -3 plus 3. You already figured out it is 0 over 0. 9 minus 3 is 6. 6 minus 6 is 0. Now, hold on. How do I drill keep going into your heads? I just say it over and over and over and over and over again? No, conic section test proves that doesn't work. Or else we would have remembered more of our formulas. Anyway, so make you write the whole phrase, keep going, with an exclamation point anytime you write 0 over 0. Better, kind of tedious. So instead, K, G. Keep going. Anytime, every time you write 0 over 0, which you need to do as the beginning of any of these problems, because you have to start by plugging in first. Because, once again, just because there's a 0 in the denominator does not mean that you know what's going on unless you look at the top 2. So the first step would be to plug in, to show me 0 over 0, and then to write KG. And what does KG stand for? Keep going. How? I know, low Santo. I'll play with the air in just 1 second. How? Well, wait a minute. There's a polynomial on top and a polynomial on bottom. I have a quadratic and I have a linear, right? Polynomial, polynomial, sweet. What did the note say? Divide out. How? Either factor or polynomial division. Yeah, let's see if we can factor. It's a quadratic, right? And there's a 1 in front. It's an easy quadratic. Okay, so how do we factor the top? Who's already got it? Careful. We need factors that multiply to be 6. So it could be 6 and 1, or 2 and 3. Are we good? -2 times +3 will be -6, and -2 plus 3 will be 1. Now, why is that so great? Wholes are removable because for polynomial expressions, top and bottom, wholes always have shared common factors. What can we do with shared common factors? Simplify. Now, if this was the function, I'd have to put a little like, okay, x minus 2 such that x is not allowed to be -3. But for a limit, I don't care whether or not there's a hole or not. I don't care whether or not they're getting breakfast. I just care about the approach. And guess who's all about the approach? This guy. This guy is just saying ignore what's going on, like when I went up and when I erased. It's just missing. It's just missing. Was there a hole? I don't know. Was there not a hole? I don't know. I just erased it, so who knows? So I'm erasing the factors and just saying, sweet, what's left? X minus 2. Am I going to have any issues plugging into x minus 2? And the answer is no. Dun, 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 dun. Guess where this function is going when x approaches -3? -5. That's it. Now, here's something I need to point out to you really quickly, though. I'm going to go ahead and move this down just a little bit. And I'm going to write the limit as x approaches -3. Oops, nope. The fraction's gone when we reduce. Just in case a few of you guys went a little too fast. What's left is x minus 2. And then plug and chug. Now, Here's a question. Here's a question. Was it important to write the limits where I wrote them? What do you guys think? Was it important that I rewrote the limit 2 times? And if it is important, why didn't I rewrite it more? Technically, this is an equals. Technically, that is an equals. Technically, that and that are equals. Why are limits there, but not here? Was it important, or do you think it was random? Was it important, or do you think it was random? Can I show you something that has something to do with this, but it has nothing to do with limits? It has something to do with the notation, but it has nothing to do with limits. Ready? What if I was to show you the following? 2 times the square root of 3 times the quantity, parenthesis, y plus 1, equals 4. Okay? Not a limit problem at all. But it has something to do with the question I just asked. Was it important where I wrote the limits, and why didn't I keep writing them? What do you guys think would be the first thing that you would do to solve? Yeah, that's what I was thinking. Divide by 2. Right? If you divide by 2 and then you rewrite, you would have the square root of 3 times y plus 1 equals 2. Now maybe some of you would do something differently than I will, but okay, just hold on. It's for sake of the illustration. Next, I'm going to distribute the 3. And I'm going to have the square root of 3y plus 3 equals 2. Now what? Why are we squaring? Okay, because the square root has a purpose. And once I square both sides, what's true about the square root? There's no longer a purpose, and actually it would make it wrong to keep rewriting it. Now I'm just going to do a dot, 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 because it doesn't really matter how I finish the problem for the sake of illustration. What am I trying to show you? Why the original problem had a square root? Why did I keep rewriting it only there and there, but I didn't rewrite it here? Not only is there no point, but the square root has already been dealt with. Was it important that I kept rewriting the limit? Yes. Why? As long as the x remained, I needed the limit to remain as well. I can't just take away the limit, because the limit of this function does not equal this entire function. Doesn't even necessarily equal any part of it, because remember there's a whole. I need the limit to remain with the function until I plug in. And as soon as I plug in, there is no purpose to writing the limit. As soon as I plug in, there's no purpose to writing the limit. Now, did this plugging in work? No. But it did give me a direction. But I was still plugging in. There was no purpose to writing the limit. The same reason that you can't just randomly stop writing a square root just because you don't feel like it. You can't just randomly stop writing the limit. You can only stop writing the limit when you're plugging in. Does that kind of make sense? So just like the square root is important to keep rewriting, the limit is important to keep rewriting. And you might not think it's important, but I see this as crucial as that square root. If you were just to be like, I don't like them, so I'm just going to erase them. Dun, 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 dun. That's what I would think if you stop writing a limit. Does that make sense? And that's horribly illegal. So we need to keep rewriting the limit as we go and as we solve. Still breathing. Okay. Even smiled. I'm not sure if that's good or bad. I already checked all the Twitter feeds, though, from the East Coast because they finished hours ago. Anyway, this one was not too bad because the factoring was nice for most of you. Then as soon as we canceled out, then we could plug in and we were done. So this guy, what do you think? What should we do first? Plug in. I love it. That was perfect. Plug in. And I plug in, I know some of you are really good at mental math, but I want to see it. Now, you don't necessarily need to actually show 1 to the 4th minus 1 over 1 minus 1. But what do I want to see? 0 over 0. Keep going, right? 0 over 0, keep going. 0 over 0, keep going. How? Some of you are great at factoring. Can you help us? Because some of us aren't. Some of you guys are great at factoring. Ooh, x squared. That's a good idea. Why are you doing x squared? Yeah. X to the fourth minus 1 is actually a difference of squares, which is super, super, super nice. Now, hold on. Can I go canceling anything? No, because if I put parentheses, it doesn't match. But there's another difference of squares. So can I make it? Okay, remember, with the plus, it's completely irreducible. I can't do anything with that. The zeros are imaginary. Stop, stop, stop. But this guy, ooh. This guy. More people still breathing? No, it's okay. Let people come in. They're just getting there forever. Okay, you can still say it's difficult. You're still breathing.
Got raped, Misty.
Oh. That's a little extreme. It was good? That's what I heard. Was AB the one with the escalator?
We got escalator.
You got escalator?
The escalator was pretty easy though, but I didn't know D was an escalator.
That's okay. D's are hard.
And then
Caitlin, it's okay. It's okay.
That was the first one.
and I saw it and I
Pull
was
them out
like,
eventually, yeah?
I know this.
Do you guys see what they're doing? Calculus kids, does this come back? Dun, dun, dun. What happens when you get 0 over 0? There we go. We got 1. It's okay. The rest of them will say, I said give them a chance. Give them a chance. Well, they don't know how to do that. It was on the FRQ, though. All right, now that it's recorded that we're doing something illegal. Let's come back. Pre-cal kids, what do you see? Yeah, reduce. What happens when you reduce out the whole for a limit? When you get 0 over 0, keep going. What can we do now? Keep going. Yeah. How? I can rewrite it if that makes it nicer for your brains. How do we keep going? And why am I going to stop writing the limit? Because I'm going to plug in. So I can do 1 squared plus 1 times 1 plus 1 equals dun 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 dun. That wasn't bad. Now, what if someone saw this and they're like, I don't know how to factor x to the fourth minus 1. Look at the stuff above our examples. Dividing out method, either factor or divide. Ooh, is there a way to divide? Some of you were totally able to help me out with this and to factor, but what if we didn't know how to factor? Could we have put, why am I putting zeros? Because I can. Yes, because I can, and I need to hold the place just in case. Ooh, that kind of rhymed. Could we do polynomial division? And the answer is yes. And what would happen if we did polynomial division? Can't you do a little? Now, I'm going to go kind of quick. Some of you need to review maybe polynomial division a little bit. But remember, I see how many times x goes into x to the fourth. I do some distributing action. It's division, so I subtract. I multiply by a negative, so I don't kill a seal. I end up with 1x cubed plus 0x squared plus 0x minus 1. I go again, seeing x into x cubed, x squared times. I distribute again. I now distribute my negative. Then I add down. Then I see x into x squared x times. Oh man, this is tedious, huh? Is it nice if you can see how to factor? Yeah. Whew, but what do I get? One more? No, it's a good thing, isn't it? Because aren't they going to cancel? What's this guy? What did Zach just do? It is 4, but what did he just do? Because he did important math that some of you would have been like, I have no idea. He said, no. Didn't Zach do 1 plus 1 plus 1 plus 1 is 4? What is that? Wait, if you divide this guy by this guy, you get this guy. X cubed plus x squared plus x plus 1. Plug it in. 1 plus 1 plus 1 plus 1 is... How are these the same thing? Guess what would happen if you multiplied out that guy? Same difference. Now, why did I just go through polynomial division? How many of you know how to factor that one? It's the sum of two perfect cubes, and there is this special SOAP, same, opposite, always positive, like formula that you could have memorized at some point in your career, but most of you have no clue how to factor that. So what are you going to do? My advice, it's not a difference of squares. I can't that way. My advice, what am I going to put in the box? Plus 0x squared plus 0x plus. You're going to divide by. Is it going to work? Yes. Why? How do I know it's going to work? Oh, I did a grave mistake. I didn't plug in first. How do I know the division is going to work? Because this is a 0 over 0, and what can I do with 0 over zeros? Keep going. And if you don't know how to factor, what are you going to do? Divide. And when you divide, you'll get something new, and that something new, you'll go ahead and say, ha-ha, I can do the limit of I don't know what with the limit of whatever answer I get and plug in. Now pause. Can you start 12.2? Yes. Will there be other problems that come up? Square roots? Oh, that's still a square root. Complex fractions? There are two types of non-well-behaved functions that we haven't gotten to practice today, but that's why we still need to finish section 12.2 tomorrow. But what type of problem did we do? Polynomials, top and bottom. When you get 0 over zeros, you... I can't let you leave. When you get 0 over zeros, what do? Keep going. Factoring or dividing. Start homework tonight. I'll see you tomorrow. Bye, toodles. Wait, we have one more minute? Oh, I could have kept going. Oh, all right. You guys sit and chill. Don't get up yet. I'm just going to keep going on my polynomial division. And you guys can check it tomorrow. Well, because the East Coast has been doing it for like 3 hours. I was looking during BC and they were already all up. Was it BC that got plankton or was that AB?
BC got it. I don't know if they did.
Okay. You didn't get plankton? Who got the coffee? Oh, some other version of the test had coffee. Because Jason put like tea, so I thought he might be close to coffee. But oh, you got coffee. AB did.